Hello, everyone. Welcome back to the Development Diary of Saikyo, the cross-platform language learning app. Last time, we were in the middle of defining our fixed width integer types, and we also created a memory arena. And we also created these convenience functions, so that way we could quickly do the math automatically to figure out how, like, if we wanted, say, 3 kilobytes, how many bytes this would become, or 3 megabytes, how many bytes this would become. So we did a whole bunch of prep work, and I said in the last episode that we would begin coding of UI proper in the next episode, being this episode. So that's what we're going to do. What I'm thinking is this time we're going to go through and we are going to actually make the function calls inside of this function. If I quickly add in my footer as well, we're going to make these happen and produce something inside of the composition. So if you're following along, get ready to see a little bit of memory management, manual memory management. And without any further ado, let's head. So one thing I did notice is I never ended up passing our composition thing that we created here, UI comp. So we should go ahead and add that in. So we'll add that in. And this is that. Awesome. So I wanted to execute this, and I just want to see, kind of build up this mental model in my picture of what happens when we go through the code. We execute the code. So we come into UI, we hit this compose function to begin with, and then we're just going to descend into it. And obviously here, nothing is happening. So this is a good place just to start off. So let's go ahead and we need to stick some data into this composition object that we're passing around. We have widgets, we have widgets, which is our memory arena. So we know we're going to need to pull this out. So we can say here, that arena will be a pointer to the widgets. As you can see, C-line knows that this is a memory arena. And so this function thing that we're getting passed through the call site, this is the builder function, which will keep recursing and go through many iterations of compose. So we know at some point we're going to need to call this thing. What arguments did this pass? Did this take? So nothing. So I will force this now to, actually maybe not, because we're capturing it here. So we'll just call the widget thing with no arguments. Although, you know what we could actually do? We could do this, where we'll say that when you call this function, not only do you pass in the function to call, but you can also optionally pass in, I always forget the syntax for this, optionally pass in arguments. Usually in C++, when you have a template like this, if you've never seen this before, what this does is it creates a C++ style variadic function where after the widget argument, you can pass in 0 or more extra arguments. And this ... signifies that when you pass this through down to the function, you say args ... on the right side, and this will expand to a comma separated list. Naturally, if you don't pass in anything, then even this syntax, even if you use the syntax, it will just evaluate to nothing. So when you call this function, you can pass in, say, 1, 2, 3, and then you would have to pass in int. And at this point, then it would be completely okay. But I don't suppose we'll do that. It's really just in case you didn't want to capture something. For example, if you didn't want to use lambdas, then you could do this. It's a convenience thing more than anything. Okay, so we'll pass this in composition. There is one thing we will need to take. We will want to take in something which is the current widget. So I will need to define a kind of widget quote unquote base class, but it won't really be a base. It'll be just more like a prototype. So I guess we'll call this a widget. And the most basic things that you need to have for UI is a position and a size. So let's add those in. because I do have a bit of experience with this, I do know that we will probably want to have the position and size themselves be structures. So I'm going to call the position thing offset. And you might think that you would stick in 32s here, but in my experience, it's better if we go from the start, just making everything floating point. And the reason for that is because almost certainly for block widgets, things that are a flat color and just squares, this won't be very important. But when we start to add in things like widgets that have curved boundaries, or we start to deal with SVGs, like this H is probably an SVG inside of C-line, or we start dealing with text, they won't snap to a pixel grid. Text, when we eventually do text layout, the text itself will take up a non-integral number of pixels, or subpixel precision as it's called. So just in preparation for that, we're going to make everything floating point. And it's not going to be too big of a deal anyway, since all modern hardware has dedicated floating point hardware. So it's fine. So we need offset. We'll also need the size. Now, I'm tempted to call this size, but this is too generic of a name, and I know that this will conflict with other things like AppKit and probably, no, I think maybe UIKit as well, although I could be wrong about that. But we're going to use another commonly used name for this struct called extent, and we'll do the same thing. So we have XY, and then we have W and H, width and height. And our convention will be that the coordinate space origin will be top left, and then positive x is to the right, and positive y will be down. Can I do like, haha, emoji power? Probably then I could do, let's see here. Haha, look at that. Perfect. So positive x to the right, positive y is down. So we'll stick these inside of our widget here. So we'll have an offset, this will be pos. We'll have extent, this will be size. And we will probably also need to have some kind of color. And so we'll define that now as well. So with our color, we'll also use floating point colors, even though hypothetically you could define your colors to be in 32s and then a color, to be in 8s, then your color would be 32 bits or 4 bytes. But also, just from experience, it's almost certainly a better idea to have the colors be float 32s. And that's, I mean, it's pretty, how would you say it? It's more of a preparation for things like if you wanted to do like high definition range stuff, which is like completely way into the future. But having this kind of prep thing is just nice. Also, it's just easier to work with all of this data when the types are the same. So with that in mind, we will make our typical color struct be RGB and A as float 32s. Awesome. And we'll stick that in here as well. We will probably want eventually things like a background color and a foreground color, for example, for text. Although even that's questionable. There's many ways we could do this, and that probably sounds quite nebulous. We're going to build up to that. For now, we'll just make our widgets have a block color. And then, so if we know that we have that, we'll need to actually make a widget down here. So we'll call this W. Or what we'll do is we'll call this widget function. And we'll make a widget thing here be a widget. And we'll initialize it to 0 because we're expecting that this widget function will fill in our widget for us. So we'll just pass it the address of the widget. Which now means when we come back over here, all of these functions are now going to need to take a widget pointer. Awesome, so I'll just call these W, W, and W. like this. And we have an error here. What is this error? There's no matching function to a call of type of this lambda. And the instantiation of the function was requested here is broken. Ooh, what happened? Did I accidentally pass in the widget itself? Yep, I meant to pass in the address of the widget. Are you okay? You're not okay? That should be okay. I think maybe, well, let's see here. Let's see. Oh, it looks like it compiled just fine. No, instantiation. No, non-void function does not return a value. Oh, that's because, right. Here we're returning a void star, but we haven't actually returned anything. So I suppose here we'll also return the, well, we can't return the address of widget, can we? Well, to be honest, we don't even want to have widget be on the stack. We want to allocate widget from our memory arena. So let's go ahead and let's do that. Now, I think I did say that I want the widget memory arena to be linear. So what that means is we start at the start, right? We come down, we maybe make an allocation, until we get to the end of our pre-allocated memory inside of arena, and then we would either fail there or we would realloc. So we won't have to realloc right now because we've given this thing like I think 8K or something. But we will need to start allocating out of it. So let's go ahead and do that. I think I'll make a function. Just close all of these. I will make a function. And let's call it ln_alloc for linear alloc. And it will take one of our memory arena things. We'll call this ln for linear. And it needs to take in a size. But what do we mean by size? When I write these kinds of allocator functions, I do like to make them a template, and I templatize, I parameterize this function on a specific type. And instead of here putting the size in bytes, I will make it a count instead. So that way, when you alloc, you think to yourself, oh, I'm allocating 1, 2, 3, 4, n many copies of a t, like this. And it makes it easier. Instead of returning a void star and then having to cast it, we just do the cast inside the ln alloc. It's a quality of life improvement. So we return a t star, like this. And because a linear allocator just allocates one after the other, you can't free anything from a linear allocator unless you free like a whole chunk from the back to the start. So I will make the equivalent of an ln free, but instead of this being like, oh, pointed to a thing, instead what this will be is to a uint32 to a checkpoint, which will just initialize to be 0. And it's actually easier to write this one first. So we'll just reset the current back to the checkpoint. So if you ln free, by default, it will just free everything. It will reset our cursor to where we are in the allocated array back to the start. And obviously the caller of this function can take a checkpoint wherever they like, pass in that checkpoint back to peel off parts of the allocations that they no longer need. So it's much more like a stack in that regard rather than a general memory allocator. But I also like to default this t to be a uint8, so that way by default it will just allocate bytes. Although I don't think this will work. I think if you do that as a default anyway, you still have to like do this. So, doesn't matter. Let's write this function. There is one more argument that I always like to pass in with this, and that's the alignment. and the alignment will default it to be the alignment of t. But sometimes you want to over. So the reason why this is important is because if you just naively say actually we'll do this with an example. Say you allocate a UN16 and then you allocate a UN32. Well, this is going to be 2 bytes. It will leave the current to be on 2, and then if you try and just naively allocate 4 bytes after it, it will put the current on 6, and this UN32 will be on a 2-byte boundary. And on some architectures, that can cause a major performance hit. Sometimes it makes the processor throw an exception. You don't want to do that. You want to make sure that your types are properly aligned. And by default, malloc and friends, they will align on the size of a pointer because historically nothing was bigger than a pointer. But now we have SIMD, and with SIMD you can have things that are bigger than a pointer that still need to be aligned. The vector registers, for example, can be like 128-bit or 16-byte aligned, etc., etc. So the C++ library have aligned alloc. We're just going to sidestep that and just take in the alignment directly here inside of our ln alloc. And so the user of this function can change the alignment of the memory if they want. But other than that, it's the same kind of easy allocation that you would potentially think. So let's go ahead and write it first. We'll just grab the current. So we'll grab current, which is ln current. And what we want to do is we want to figure out how many bytes we're going to need. So we'll need at minimum, we'll need the size of t times the count, but then plus any extra alignment that we need to calculate. So the easiest way to do that is this. So we'll do required bytes. We'll take current, and what we'll do is we'll move current up to the next alignment point that it needs to be. So the way that we do that is like this. So we'll say current plus, what's the easy way to explain this? I kind of wish I had like a whiteboard or something. But essentially what we want to do is, what we're kind of expecting is alignment to be a power of 2. And that's important because we can do this kind of trick. We can say current plus the alignment. So that'll be big. And then what we'll do is we will AND this with the alignment -1 and flip it. Unless current ANDed with alignment equals 0, then it will just be current. So this probably looks like a soup of just weird random bit twiddling stuff. Sorry, it's this way. So what is this doing? What is this doing? Let's start with this first expression. So if current, it's probably be easy to see like this. Let's say current was 4 bits. So if current was OB1100 and the alignment equal 2, which is OB10, then when we do a bitwise AND with this, this will be equal to 0. And what that means is that, what is this? This is 1, 2, 4, 8. So OB11 is equal to 12, I think. So 1, 2, 4, 8, yeah, it's 12. Is 12 divisible by 2? The answer is yes, and that's what this is testing for. We're testing to see whether or not current is already properly aligned by alignment. If it is, then we don't touch current, we just leave it alone. But if these are not properly aligned, then this will be equal to... wait, hang on, I think I've made a mistake here, because this will still block out the wrong thing. Hang on, let me see what I've done here. So current with alignment minus... I may have to actually do this. I've written this code many times, the alignment code, but I always forget the specifics of how I do it. If alignment was 2, then if we took 1 from this would be 01. And then if we end this with 01, then this will be 1, which implies that 13 is not divisible by 2. It has a 1 remainder, right? And that's what we're checking for here. So when this is not aligned properly, then we'll do this incantation, where we'll take, let's keep the case where current is equal to 13. So if we do 13 plus 2, this will be equal to 15, which is OB1111. And what we want to do is we want to essentially bring alignment up to, bring current up to the next highest multiple of the alignment, which in this case should be 14. And so if you know your bit math properly, what that would be is these 3 bits being all 1, and then this bit being 0. So by doing 13 plus 2 equals 15, we get all 1s here. We want to knock out this 1. If you look at this, when we take 1 from the alignment, which is what we're doing here, then this would become OB01, or it's just 1. And then by flipping this, this will become OB0. And if we end OB0 with, which if we extend it, it'll be 4 zeros. Sorry, no it won't. If we take OB0001 and we flip it, this will be 1110. And so by ANDing OB1110 and OB1111, we will get OB1110, which is equal to 14. Because this is 2 plus 4 plus 8, which is 14. And so that's what this trick is essentially doing. We're moving current up to the next multiple within the range of the next multiple of the alignment, and then knocking out the bits which need to be knocked out for current to land onto an exact multiple. It's we're just basically rounding up. And this kind of thing, it took me a while to fully understand it the first time, but if you stare at it for long enough, it does start to make sense. Which actually perfectly explains why we would need to do this check here like this. Because we're basically checking to see whether or not it's already aligned with the bitwise complement of the alignment minus 1. So this definitely can confuse people, but it's kind of like you're overfilling a bucket and then throwing out, you have something less than a bucket, you're going up to the bucket and a little bit more, and then you're throwing out a little bit more and just going up to the threshold of the bucket. That's the intuition behind this expression. Okay. Anyway, if we take current now, plus our required bytes, if this is now if the capacity is less than this, which is to say that current plus with a properly aligned current plus the number of bytes that we need, if this is greater than the current capacity, then we will have overflowed our memory arena, which is not good. So we should, I don't have assert here. I want to avoid this case happening, so what we'll do is we will assert that this never happens. You would think you might return null pointer here, but here this for me will be a straight error because we're doing a lot of pre-allocation. So I want this to straight up die when this condition happens, which is why we're using assert for now. Awesome. Okay, so assuming that this passes, then our current now will be properly aligned, ready to give us a T. And I should probably also check that alignment, the alignment of T is a multiple, that alignment is a multiple of T. So I guess we'll put this here. So I want to check that the align of T is divisible. Okay, that'll check that. Cool. Now, assuming this is correct, then we'll get our pointer, which will be the allocator's bytes plus current. All of this cast to be a T star. And then we'll move our current pointer to the allocator's current to be our aligned current plus the required bytes, right? Because we moved it up and also actually gave the necessary space for pointer. And then we will return pointer, just like that. And our allocator should be doing the right thing. So back with our widget, now we can allocate it, just like this. We'll say ln alloc, our widget, and we'll pass in our arena. And by default, count will be 1, so we're only allocating a single 1, so that's okay. Just like this. And then we can pass the widget function widget, and we'll also return a widget pointer here. So that way, even outside of each of these functions, we can get a reference to this widget thing that we allocated. And I think I will also need to, no, I won't. I think this is the only instance of our function, and it is. Cool. So let's give this a quick execution, see what will happen. So we jump into compose, we grab out our arena, jump into our allocator. What is current? Current is 0, unsurprisingly. Is 0, is our alignment, which is the default alignment, divisible by the alignment of T? The answer should be yes, and it was. So current here should be, after we execute this, current should still be 0, and it is. So the required bytes should be the size of our widget times 1, which is 32. Does that make sense? Where is widget? So we have 1, 2, 3, 4, 5, 6, 7, 8 floats. 8 times 32, or 8 times 4 bytes is 32 bytes, and that's exactly how many bytes that we need. So it looks like that worked. This should be okay. It was not. Why are you not okay? Our capacity, assert that our capacity is less than, sorry, if it was an if condition and we would thrown, that would have been what I wanted. But here, what I want to do is I actually want to assert that these two together is less than or equal to the capacity. Yeah, that's right. Even if we align current and add in the required number of bytes, if we go up to but not over the capacity, that's okay. It means that we've tightly allocated the remaining memory, so that's okay. Come back here. Do we pass now? We do. Grab out our pointer, which should be completely all zeroed out. It is 0, 0, 0, 0, 0, 0, 0, all good. We move up the allocator's pointer. That's awesome. And we return the pointer. Then we'll call the widget function, which does absolutely nothing. But it looks like we did everything that we want to do correctly. So, yay for us. Awesome, awesome. Sweet. So we're in a good position now to go and start filling in our widget, but that's all the time that we have for today. So this has been a little introduction into linear memory allocators and how to do it, and also getting our UI started properly. So probably the highlight of this episode is that this example is how you do a bitwise roundup when you know that this is going to be a power of 2. If that was confusing, then drop me a comment or ask a question, and I'll try and revisit this again, maybe give it a bit of a better explanation. But thank you so much for watching. In the next episode, we're going to continue on with our UI programming and start filling in our widget. But until next time, take care.